So now we have Barbara Castanheira from Baylor University, who's gonna tell us how to listen to the stars. Barbara, take it away.
Yes, thank you. Hi, everybody. Sorry. Well, first of all, I'd like to thank very much for the invitation to give this talk. And I'm for one of those people who don't prefer to do things remotely, since I am a mother and I have kids and I have to deal with all of that. And I had to move because there is somebody putting a door inside my house right now. So that's always, there's always, I can't wait to come back to normal life, or at least that I can actually go to conferences. So anyway, so today I'm going to be talking about astroseismology of white dwarfs and how we can listen to stars. You probably you heard some instruments going on. I hope I can show to you and make an analogy of the differences and what we can truly learn from that. Every time that we start giving a presentation, we want to put a pretty picture in front and in the first slide. But of course, the pretty pictures of white dwarfs are not necessarily very pretty. So because it's just a star by itself. So I actually have a pretty picture of what will become a white dwarf. So here we have a planetary nebula. And this planetary nebula is still ejecting its outer layers. So this is a pre-white dwarf right at the center here that we are looking at. But if I want to really see a white dwarf, we can actually look at a picture from Sirius B. So this is Sirius A. We can all see Sirius A from Earth. It's a very bright star. Sirius B, we actually stumbled across it. And that's how white dwarfs were first discovered, because we were actually seeing the gravitational influence of something on Sirius A. So Sirius A was actually moving in the sky a little bit. And that motion, we actually calculated and attributed to a body that we were actually should be orbiting that star. So that's how we first discovered white dwarfs, and we call them white because they were white, right? And dwarfs because they were tiny in comparison to the main sequence stars. Now, I'm not going to be talking about white dwarfs in general, but I'm actually going to be talking about pulsating white dwarfs. So this is another one that we basically stumbled across, and this is HL Tau 76, which was the first DAV ever observed. So Arlo Landot was actually making a catalog of standard stars and studying the variability of those, studying actually the photometry of those stars. And what he actually measured here for this particular star was that in this plot we have here modulation in milli-amplitude, so it's something as intensity of the star as a function of time. Okay, and then you can see here that the star is actually changing its brightness over time. So then we found this to be, and it's cyclical, it's repeating itself. So we started seeing, maybe this is not a constant star. The first pulsating stars that was discovered is a class of stars called the Miras, and they were miracle stars because they were changing their variability. And we could see that with naked eye even. But the time scales were completely different. Those Mira stars actually pulsate like this. They become bigger and smaller and bigger and smaller, and we can see that change. For white dwarfs, as here, it's the milli modulation. So the amplitude is very, very small for us to detect with naked eye. So we really have to go ahead and see, with very precise instruments. So naked eye, we would never ever be able to detect these pulsations. So fortunately, there are some questions in the chat. I don't know if I should answer. Oh yes, I'll go back to the, thanks JJ. Thank you JJ for answering. The DAV is the one that has hydrogen. So JJ actually showed the spectra, how we can get spectra of those stars. And here we have two columns of spectra. So the DAs, which are the most common white dwarfs, so something like 80–90% of all white dwarfs will be DAs, which means that in the photosphere of those stars, we still have a lot of hydrogen. As JJ also mentioned before, there is the gravitation settling, so everything which is heavier than hydrogen has already sank down towards the center. So in rough terms, these stars are carbon and oxygen in the center, helium and hydrogen outwards. So we have here some additional types of things that can be seen on those DAs, which come DAs that generate hydrogen. We can have magnetic field, therefore we have an age here. So the effect of the magnetic field on those hydrogen lines will split, oh, so sorry. They will split them. We can also have Z's for metals, we just heard about that. And some white dwarfs may have a companion. So this, the bottom one is a DA with a main sequence star. So this we see the component of the white dwarf and then the component of the main sequence star. The second most common type of white dwarfs is the DBs, and the generate, B stands for helium. So whenever the protoplanetary event happened, the star ejected pretty much all its hydrogen as well. So there is basically carbon and oxygen and then a thin layer of helium. And we don't see any hydrogen lines here. So we see a very similar similar spectra here. So the DBs with magnetic field, the DBs with metals. This is an interesting one. It's a DB with a tiny, tiny little amount of hydrogen, so DBA. And we have here, again, on the bottom, a DB and a main sequence star. So we are mostly talking about DAs or DAVs, because those are the white dwarfs with hydrogen that pulsate. But we also have DBVs, we have DOVs, and so on. So you probably heard about the Gaia mission. The Gaia is a satellite that will have a goal of observing billions of stars. And by these observations is actually measuring the distance and doing photometry of those stars. So you can measure distance with parallax. And so we measure the stars, compare them with the background stars and try to determine the distance of those stars, as well measuring the photometry. And by doing so, we are able to make this kind of plots for stars. And this is the plot that comes straight from the Gaia mission, which has lots and lots of stars. And we astronomers like to organize things, right, by brightness. So on the top here, we put the brighter stars. And then we also organize those things based on colors. So on the bottom here, we have bluer, and to the other end, we have redder stars. So stars don't fall in, we think this plot with luminosity in the y-axis and temperature in the x-axis, we don't find stars randomly distributed. They actually fall into those very specific sequences. So this is the main sequence, which is where we see most of the stars. We also have giants and supergiants. And then we have this faint and hot sequence, which is where the white dwarfs are found here. Okay, so you see this is, and another thing is about pulsation. So what are the stars that pulsate? I talked to you about the Miras, which were the ones that actually pulsate, but we see inside this HR diagram, this diagram is called HR diagram, we see that there are pulsations throughout all the evolutionary phases. So this is, let me just point out, this is the white dwarf cooling sequence. And as the stars are cooling down, when white dwarfs are basically cooling down, they will cross those instability strips. And they will show variations on their brightness depending on the element that is dominant in the photosphere of the star. So in this case here, if the white dwarfs have helium, then we'll have them pulsating at these temperatures here between 30,000 and 22,000 Kelvin. If they have hydrogen, they will pulsate in a very narrow instability strip starting at around 12 1,500 Kelvin down to 10,000 Kelvin, basically, very, very narrow. Sorry. So what are the types of pulsations that we have? So for most of the stars, we're going to have two types of pulsations: gravity waves, G modes or gravity modes, or pressure modes. So pressure modes are like the sound. So we have, for instance, the pressure is a longitudinal wave that propagates like that. So that's how we decide, that's how we claim this to be pressure modes. And gravity waves are transverse waves. And they're basically the ones that we observe, for instance, in water. There are basically two types of pulsations that we can observe on stars. So the stars can actually pulsate radially, so they change the size, or we can have the pulsation non-radially, that it will go through the star. But what can we really learn about pulsations? It can tell us, for instance, the composition of the star, the type of the star, and so on. Now, I actually have at home a guitar, and I'm just going to show you here a guitar, if you don't have it at home. And I also have an ukulele, okay? So they are basically the same instrument, right? But this ukulele is a shrunk version of the guitar. So if I play the guitar in one string here, let me just show you. So this is a, see, everybody can hear that. If I plunk one of the chords here, oh, sorry, it changes the sound. And I have other chords here that will sound differently. And if I look at the chords, I don't know if you guys can see very well, they're made of different thicknesses, so that's why they sound completely different. So I can identify by the sound that I'm producing with the guitar that this is coming from a guitar. So now if I want to play an ukulele, sounds a little bit different. Okay, just get a little. So this is a smaller instrument than the other one. And this is the same analogy that we are doing for stars and pulsations on stars. If you can hear the frequency, or of course you cannot hear the frequency from the stars, because that's not how electromagnetic waves will travel. But if we detect the frequencies, we can tell this is coming from a small star, this is coming from a big star, this is coming from a star that has more carbon, less carbon, more hydrogen, less hydrogen, and so on. Okay, so that's the basic idea of doing astroseismology. Let me check, there is some questions. Okay. All right. So the non-radio pulsations that we observe on white dwarfs will look like those light signals that will travel. The light is traveling here. So in this diagram here, we are seeing kind of one darker region and a fainter region. So we have orange and yellow. So this is basically a difference in temperature. And we are seeing that it doesn't deform the star. It doesn't change the size of the star. It's just that the wave is traveling around the star. This is something that Mike Montgomery does quite a bit. I stole it from him this here, which is modeling the amplitude of the pulsations. So what we are seeing here, the star is now fainter, and then it will become brighter again. So we have here one spot traveling around the star. And this is basically what's happening here. And it's well identified, the blue one, so the waves are doing this, but it's not really changing the size of the stars. So what is our understanding on pulsations on white dwarfs? We actually, when we do observations, we see that there are two types of light curves and very distinct ones. So we have this one here that is very peaky in terms of the shape of those, the pulse that we are observing. And we have the other one that is very sinusoidal. And we also see that the sinusoidal one has a smaller amplitude and the other ones have a bigger amplitude. So what is our idea? And again, back to the understanding of the pulsations. So it happens in a cavity where the cavity, like the cavity of the guitar, the body of the guitar, right? So there is a cavity here, and this cavity is changing, becoming bigger as the star cools down, and it's also becoming deeper. So that's why the pulsations are basically a way for the star to release energy. So that's a way that the energy is being transported from the interior of the star outwards. So the stars are cooling down, and then therefore the internal structure of the star is changing. So there is convection in those layers. So the convective cavity will actually deepen and becoming bigger. So that's what we are seeing here, and that's why we have the differences between the hot DAVs and the cool DAVs. We also call DAVs ZZ Ceti, despite that the first DAV that we discovered was AGL Tau 76, and the second one was the ZZ Ceti. We named the class after the ZZ Ceti, so I don't know what, I mean, I honestly don't know why. But our understanding of the mechanisms that drive pulsations is so great that back in the 80s, Don Winget, who was my co-advisor, the advisor of Mike and the advisor of JJ, he actually predicted that this is happening because in that cavity that we observe for the DAVs, hydrogen is becoming partially ionized. So the hydrogen, when the star is very hot, is fully ionized. As the stars are cooling down, we start to see some of these electrons recombining into the atom. So he thought, maybe this is equivalent to the reionization of helium. And he went on to look for pulsating white dwarfs that had just a photosphere of helium. And he looked for them, so he made calculations, predicted the temperature, and he was looking for them. So he had like a program at McDonald Observatory, and he, at some point, he said, well, why don't we look at the brightest one? So GD358 is the brightest pulsating, the brightest dB, and it's also the prototype of the class of pulsations. So that's a very powerful thing to say that we really understand the mechanisms that will drive the pulsations. Now, when we are actually doing astroseismology, instead of looking at the light curves, we actually do a mathematical process called Fourier Transform. So instead of looking in terms of time as a function of intensity, we go to a different space of frequency as a function of power, okay? And or amplitude. Sometimes we'll see amplitude here. So when you do this Fourier transform, everything that we are seeing here in this graph is what we call the noise, right? So everything above this line here, so we set a limit, a detectability limit, to see how those are real pulsations of the star. So we have to, first of all, detect the pulsations of the stars, and we have to, our models usually use independent modes. So we will see when we have pulsations, we'll see harmonics, subharmonics, we'll see linear combinations and so on. But we just want to actually look at the independent modes, and we will compare them with models. And then we determine the stellar structure. So it's a simple process, right? The problem is most white dwarfs will have very few pulsation modes. So in this particular one, G117b15a, we have only 3 modes. And if we have 3 things that we observe, we can only determine 3 other things. So I look at this plot here at the bottom, and we want to see the amount of carbon, the amount of oxygen, the amount of helium, the amount of hydrogen, the temperature, the mass. And in real life, those transitions are not sharp. When we make a drawing, a cartoon like this one at the bottom, this is just a cartoon for us to have an idea of gravitation settling. But each one of the transitions will have a certain function. And we can see here the transition between hydrogen and helium. So a little bit of helium will be entering also diffused towards the hydrogen layer. And the same thing will happen here. So what if this function is a little bit steeper? What if it is like this or like that? So you can, in theory, we want also to be able to constrain how the transition zones actually happen. So we would need to observe, I don't know, 20 modes here, maybe 50 modes, the more the better. But white dwarfs don't pulsate in those many modes. So that's one of the, it's a sad thing, but again, we keep on working. There are better things that we can try to do, right? We constrain what we can constrain, right? So here is a model on top for a dB, and we have this mass here, 0.565 solar masses and 24,600, and this is for a DA. Okay, so we've found some very interesting stars, and this one here is what we call the super diamond. It's a BPM 37093, and this super diamond actually it's a little bit, there's a whole lot of stories that we can tell about this star, but mainly if you look at this cartoon that has been done, the solid part here, which is the super diamond, is at the center. So the pulsation modes will propagate only to here. So the amplitude of the observed pulsations will be much, much smaller than if the pulsation could go all the way to the center of the star. So that's why we see that this indication of very low amplitude, which actually tells us that the structure is a little bit different. Another thing that we observe here for this particular star from spectra, we know that the mass of the star is about 1 solar mass, which means it's a very dense, very small star already. So it's probably already crystallized at the temperatures of the instability strip. So in terms of the crystallization, this is not the only way that we see that, but for instance, for this globular cluster, NGC 6397, we can actually see the stars, this cooling sequence here. And I don't know if you can unfocus your eyes, but statistically, this region here is where crystallization happens, which means the stars pretty much stop cooling, and they are actually clumping in that particular region. We all know that if you boil water, whenever the water is boiling and we go from, from a liquid to gas, the temperature will remain constant. So this is basically what's happening here. The stars are cooling down, and every time there is a phase change, the stars will actually maintain their temperature. So this is the latent heat that we are looking, but for stars. And I think this is pretty cool and it's very amazing to be able to see that. Now note that the magnitude, we could only detect that with Hubble, okay, for this here, for this globular cluster. Look at the magnitude here is 26, 27. So it's really, really, really faint. So we are pushing the limits of what we can definitely see. Now, when we want to observe the stars and detect more modes, we can actually, we did this for many decades to actually, it's an interesting idea, because we can only observe the stars at night. So if you are at one site, you're going to be able to observe the stars for 8 hours. But what about trying to observe the stars for longer? So this whole Earth telescope idea, which starts back in 1990s, we were able to keep track of the star for a very long time, right? For 2 weeks of data. Open the door and tell that mommy is coming. Okay, put a mask on. Say I'm coming in and then come in. Okay. We are able to track the star for up to 2 weeks. So that was pretty cool. So we, for instance, for GD358, we're able to see many other modes as well. An interesting thing for this star is actually changed. So this is data from different campaigns from different years. So we have here 1990, 1994, 1996, and 2000. And actually, Mike coined the name for this change here. I have instruments, but he is the musician. And he actually called it this forzando, because all the energy of the pulsations was actually tuned towards one mode here, to this K equals 8. Okay, so this mode right here. So that was like the star change. And a month later, the star came back to its normal, normal thing. Now, even better than observing on Earth, we can actually look in space. So Kepler Mission was a mission designed to detect the frequency of Earth-like planets around solar-like stars. So the idea was to stare at a field for 40 years and sample 160,000 stars. Now, to get, for instance, a transit, of a planetary transit. So what actually was very cool for us doing astroseismologgy is that since you have these light curves that we are trying to detect planets, we can also detect pulsations in stars. And one of the most amazing results, I think, that came from the Kepler data was this detection of these outbursts. So this is forzando-like events also happen, but we miss them because here we have, look how many days we were able to observe these stars. So for 2 months, that's just unbelievable. That's really, really amazing. On the bottom here, we have the Fourier transform of the light curves that we are seeing here. So the black ones and the green ones as well. But now something interesting happened, unfortunate but fortunate at the same time with Kepler. So Kepler had reaction wheels, so 4 reaction wheels to keep it tracking in position and staring at the same time. So when Kepler actually, 2 of those reaction wheels failed, so the telescope was drifting down, so it couldn't maintain its field of observation. So what actually happened is they repurposed the Kepler into K2, and K2 they were actually observing with less precision, but they could point K2 at different fields, and they were able to do that for a few more years until fuel ran out, and then we were able to find even more white dwarfs. That was something very, very, very cool. And this one here that I'm plotting, I don't have a name. I didn't put a name yet because this is one that I found in my kitchen. So I can actually go into the K2 data, download the K2 data, and just keep on looking at that. So there's still a lot of things that can be done. And yeah, so we can look for data and download data all the time. And this paper here is from this year, published by mainly led by my PhD advisor of G117b15a. So this star has been observed for 45 years. 45 years. So whenever Kepler is the name of my PhD advisor, came to started his PhD, the first observing run was to look at this star. So what is he doing here? So we actually observed a period of pulsation of 215 seconds. And that period is becoming slightly longer. So it's a very stable period of pulsation, but it's becoming slightly longer over time. So it is not the most stable clock, but it's the most stable optical clock. And this is a measurement of the cooling of the stars. So now we are, with white dwarfs and pulsations, we are even able to determine the cooling times of stars. That's something that, in astronomy, we have a very hard time trying to pinpoint how the cell evolution will happen and so on, because we cannot observe a star and follow its life, basically. The time scales are just too long. But for white dwarfs, we can actually do that. The change here is very small, right? So, but it's still significant, and we can tell, the fate of this star pretty much. So that's something very, very impressive, and very difficult to do, basically. And I would like to end this talk because we talk so much about white dwarfs, and today we spend the whole day talking about white dwarfs. But if you go outside this meeting here, the most exciting things will come from supernovas, planets, galaxies, and so on. But we can learn so much about white dwarfs, and it's still the quote for the first director of McDonald Observatory, Otto Struve, was that one of the first tasks to be undertaken by the staff at McDonald Observatory be to investigate further the mysteries of the white dwarfs. And we're still doing that. So, and there's still lots and lots of things to see with the white dwarfs. Okay, well, thank you so much. Do I have any
Thank
questions?
you, Barbara. Thank you so much. And thank you to your kids for being so patient while you were giving us this lecture and talk. Okay, so a lot of new concepts have been brought up in terms of stellar oscillations and composition of the inner layers. So maybe it's time to open up for questions. I know there's been some discussions on the chat that some of us took on. Recently, people were very interested in the diamond-like nature of the inner region of some of these stars, and so the question was, how really diamond-like are we talking about? At the end of the day, these regions are so this is a plasma. These are like this ionized, so electrons are free to move. So JJ, maybe you wanna share what you answered to the BBC radio interview.
I think it was Mike.
It was Mike? Yeah, that was Mike. Thanks, Mike.
Yeah, sorry. It was so a collaborator of ours, Travis Metcalf, had just sort of did a minor story like local to Harvard. He was a postdoc there, but it was right around Valentine's Day, and so it got subsumed into, hey, giant diamond in the sky, Valentine's Day. Oh, this is popular now. And it just sort of blew up in 2003, and I was in Cambridge at the time, and so they called me. I was on the paper, but the BBC, they know their stuff. So we were doing the interview, and then the science guy said, so is this really like a diamond on the Earth? And I said, well, not exactly, because electronic bonds hold carbon atoms in certain places on the Earth, but all the electrons are just free. So the thing that's holding the thing together is that you're forcing all of them to be close, and they're just getting as far away from each other as they can. So it's not the same thing, but it's really the astrophysical equivalent of a diamond, in the center of a star. And it really is a solid. So it really is the same thing. But if you took it out of the center of the star, it would blow up because there'd be no pressure on it. It would just spring apart, whereas a diamond just sits there. So it's the difference between chemical bonds and just the electrical forces repelling each other. Anyway, I hope that helps people.
Yeah,
Mike, can I ask a follow-up on that?
Yeah.
So the diamond has a specific structure with the location of the nuclei. The question I was really trying to get at was, how is that what the arrangement is like inside the white dwarf?
Yeah, so this is a lot more compact than the diamond. So carbon itself, you can see carbon as graphite, for example, and the structure is like in layers. Then if you do the diamond on Earth, the structure becomes this cubic kind of structure. So this is much more compact than that. So it would be like cubes inside cubes if you want to have an idea. And again, I had a talk that I gave for the kids. I usually give talks for my kids' classrooms, and actually the density of white dwarfs is like a great white shark inside a little tiny playing dice. That's the best analogy, and it's great white shark. You'll never forget that. So it is like, imagine like cubes inside cubes, because you can fit many more carbon atoms inside that.
And sorry, I should have mentioned, I think we think that the interior of a white dwarf is like a body-centered cubic lattice. I actually don't know what diamonds are. So if that's the same, then they would share that as well, but I don't know. Yes,
the diamonds are cubic and not layered like graphite. So, but yeah, but they're missing. There's still spaces that you can put more. Because if you think about a cube, it has just those edges, right? But then you can put something in between them, so it's like cubes inside cubes, yeah.
And there was also discussion about the conductivity, which I thought was interesting, because in a sense, the material is as tough as a diamond, but also more conductive than graphite. So in a sense, you get both properties of carbon layering that you get on Earth, in the same form, which I thought it was. I never thought about it, but it's actually kind of interesting.
Thank you.
Okay, more questions about astroseismology of white dwarfs.
I saw one question here on the chat about the optical clock. Yes, we correct. Yeah. We correct for everything, even from the motion of the barycentric motion of our solar system. So we correct everything. So this is purely coming from the motion, relative motion of the star for everything that we are seeing. So it's corrected, yeah. And this is purely from the pulsation of the star.
And Barbara, I mean, for this type of pulsation, since the period is of the order of minutes to hours, I guess, you know, the frequency doesn't really change due to Doppler effect, because the orbit of the Earth around the sun is, you know, occurring on a much longer time scale. So in a sense, you know, that shouldn't matter too much. The other factor might matter, but that one shouldn't be important.
Yeah, no, definitely. But if you actually forget to correct the barycentric motion, you will find Jupiter again on the star.
That's true.
There is a hand.
Robert.
Is there any gravitational lensing from this kind of from the white dwarf, and can you see anything from that? Thank you.
Can you see the gravitational lensing?
Well, does the white dwarf cause gravitational lensing that we could see? And is there anything that we could get, any information that we could get from that?
Well, if you could use the lensing from that, you could get the information of whatever object behind that it is, right? So that would be, yeah, I mean, I don't work with gravitational lensing on white dwarfs, but in principle, if it is working as a lens, you could see whatever is causing the effect to be bigger. So, but for instance, a planet, you can find that, but I don't see much the relation with the pulsations, but any other questions?
Okay. I think people are ready to. Oh, actually, we got Mark.
Hi, just one more quick question. So if you can take Fourier spectra of the vibrations, are you thinking that eventually you'll be able to sort of map out the changes in layers or something like what you would do with FTIR spectroscopy in molecules?
So we can, by doing the Fourier transform, we can see, for instance, if the modes are beating with each other. Because if you start having tons of modes, they can start interfering with each other. So in this respect, we can see how, we can try to model and infer how the layers are going on inside the star. Yeah. So it's a good thing. It's also a bad thing to have tons of modes, because if you have tons of modes, it means that you have a lot of information. But you have to deal also with the bad part of having tons of modes, because they interact with each other, and that becomes,
and it gets way too complex to even understand.
So like the sun has, you know, thousands of modes, and then things become even more complicated. But again, it's a process. Like the more we are always trying to push the boundaries of getting better data, detecting more. So going to space is definitely better, and yeah. So, and the models are becoming better, because we have better computers. So calculating a stellar model nowadays would take, I don't know, minutes, you know, in comparison to what it would take like 20, 30 years ago, that we would have to do a whole lot of calculators spend months trying to figure out how the stars will look like. So there's a lot of development in astronomy, but yeah, things walk at a certain pace. So
Thank you, thank you.
Okay. Any more questions for Barbara? Okay, so I think everybody deserves a 15 minutes break.